My project, Servius, an object-oriented approach, concerns automatically encoding a critical edition of a complicated Latin text. A critical edition is the main text plus a set of specialized notes on variant readings. This presentation will focus on the technical aspects of automating this encoding, paying particular attention to the impact of this project on scholars from a variety of fields. The goal of this script is to turn unstructured, visually encoded data in the top picture into machine-actionable structured XML data. The important things to note here are that every section of this text written by an author named Servius has a type, and those types are implied in the formatting like pipe characters, tabs, white space in the top text. The challenge was to get a computer to pick out these formatting conventions, recognize their meaning, and encode them in a way that is meaningful to both humans and computers. So let's look in a little more detail at how I accomplished that. In previous similar projects, I've used a naive string searching based algorithm. However, I quickly realized that such a simple method would be insufficient for processing a complicated text with variable internal structure like Servius. I needed a persistent data structure to associate the type of a section with the section text and an XML representation of it. I considered other options, including Python dicts or lists, before settling on a class. I developed the ServThing class to represent the smallest meaningful subdivision of text in Servius. I chose a class over other data structures primarily for ease of use. Because a class can encapsulate type-dependent processing, the programmer can deal with any section of Servius using the same API, regardless of the section's type. Each ServThing object also maintains a valid XML representation of itself, which is updated and checked anytime the text of the ServThing is changed. Now we'll talk in detail about the data model I've chosen to represent Servius in XML. The three relevant subdivisions of the text are divs in the light green box, which are the smallest numbered subdivision, lemmas in the dark green box, and ServThings, which are the smallest meaningful subdivision of text. Lemmas are represented, as you can see, with the AB tag, and ServThings with the seg tag. My Servius script uses a nested loop structure. We start by getting a list of all the verses in the document, then, for each verse, we find all the lemmata pertaining to that verse. Similarly, for each lemma, we find all the ServThings pertaining to that lemma. Within a lemma, we split the text on a blank line to break up the ServThings. We then instantiate a ServThing for each line and add them to the lemma. In certain cases, where text is semantically related but separated by typesetting, we insert the text into the previous ServThing using the addText method of the ServThing class. This represents a significant advantage of XML editions, especially those encoded using object-oriented text representation, over print editions. Now I'm going to talk a little bit about the complexity of my script, as well as a runtime optimization I'm working on to improve it. It's important to remember that a critical edition is both the base text and a set of notes. Up until now, we've been talking about encoding the base text. Now we'll talk about the notes. Each note is represented with an app tag. And with Servius, the main innovation for my scripts is the insertion of those app tags into the main text. For Servius, we have two subdivisions smaller than the smallest numbered subdivision, so the programmer is left with the problem of finding where to put the app tag within that numbered subdivision. The completely naive solution here would be to search the entire text for each generated app tag. This is big O of the length of the text for each tag and is not viable. Currently, I'm searching for the right place for each app tag from the beginning of the matching numbered div. This is big O of a length of a small section. So while it's still linear and it's not a theoretical improvement, it does represent a huge practical improvement. There are over 1,000 divs in most books of Servius. My script can do an entire book in a few minutes, which would take the average person several days. I'm currently working on a runtime optimization that will reduce time to find the place for an app tag to almost constant by predicting which ServThing inside the div it is most likely to go in. So now I'm going to show a short demo of my script. You can see that we're encoding the divs using the nested loop structure we talked about. Now we're adding a TEI header and footer and starting on the critical apparatus. And we're done. This is a demo-sized section of text, but we have fully encoded Servius. So I'd like to conclude by talking a little bit about the impact of this script on the field of digital humanities. I think the application of object-oriented text representation is that it gives humanities scholars a more accessible way for interacting programmatically with text, specifically with XML text, which is the community standard for digitally encoded text. It abstracts away the complexity of dealing with XPath and XML syntax. I'm envisioning a user interface something like my text 127 for chapter 1, paragraph 2, sentence 7. Compare that to the XPath statement to get to the same place. Ultimately, having this user interface will make it easier for scholars to develop and use natural language processing and analysis tools, such as the Classical Languages Toolkit, which is an incredibly important piece of software in our field, but has some serious usability problems, especially for TEI text. Ultimately, I think the impact of this project has the potential to be quite significant. It will allow a larger and more diverse group of scholars to use cutting-edge NLP and visualization tools in their research. Thank you for your time.